we're going to talk about the change of coordinate matrix. Let's review some concepts behind inverses and isomorphisms. Say that we have two vector spaces, V and W, both defined over a common field F. Let's also say that V has a basis beta and W has a basis gamma. We'll say that T is a linear transformation. Recall that we have the mapping that takes a vector x to its coordinate vector square bracket x. This is a linear transformation. Similarly, given a linear transformation T, we can find an m by n matrix that corresponds to T. The mapping phi sub beta is called the standard representation with respect to beta, and the matrix square bracket T is the matrix representation of T with respect to the ordered bases beta and gamma. Later, we're going to try to focus a little bit more on how we'll actually compute this matrix representation. We're defining the standard representation and the matrix representation simply because they keep track of the scalars. For example, given a vector x in our vector space V, we know that we can express it as a linear combination for a basis beta. The standard representation just keeps track of these scalars a1, a2 through a sub n. Similarly, given a linear transformation T going from V to W, we first take the vectors V sub I in our basis beta, we then apply T to each of these basis vectors, and finally we express T of V of I as a linear combination of the vectors W sub j from the basis gamma. The scalars that we find in the linear combinations simply form our matrix representation. Now let's say that we have three vector spaces, V, W, and Z. The collection of all linear transformations T going from V to W forms a vector space. If we have two linear transformations, let's say T going from V to W and U going from W to Z, then the composition U circle T going from V to Z is also a linear transformation. Finally, if we have bases beta for V, gamma for W, and alpha for Z, then we can consider the matrix representation of the composition U circle T that we can express in terms of the product of the matrices, the one for U and the one for T. The diagram here helps to explain all of the notation and what's going on. Again, V, W, and Z are vector spaces. We have a basis beta for V, a basis gamma for W, and a basis alpha for Z. Our standard representations allow us to express the elements x and y in terms of coordinate vectors square bracket x and square bracket y. If we map T going from x to y, then we simply have a product of a matrix, that is the matrix representation square bracket T. Similarly, we have a corresponding concept for our linear transformation U. And finally, everything is connected when we look at the composition U circle T. That just corresponds to the matrix product B times A. If we have two vector spaces V and W, then the following are equivalent for a linear transformation T from V to W. First, there exists a unique function U such that the compositions T circle U and U circle T are the identity maps. Second, our mapping T is both one-to-one and onto. And third, assuming that our vector spaces are finite dimensional, the rank of T equals the dimension of V equals the dimension of W. Any linear transformation satisfying either of these equivalent properties is said to be invertible or an isomorphism. In this case, we'll say that our vector spaces V and W are isomorphic. And finally, the function U that we had up above is called the inverse of T, and we'll denote this by T raised to the minus 1. If T is an isomorphism, then so is its inverse, and the concept of two vector spaces being isomorphic forms an equivalence relation. Now let's review a little bit behind the standard representation and the matrix representations and how they're related to the concepts we're going to discuss next. Here's a specific application of our vector spaces when everything is finite dimensional. Recall that this collection LVW is the collection of linear transformations from a vector space V to a vector space W. We define vector addition as follows. Let's say that T1 and T root 2 are linear transformations. We'll think of these as rules. That is, given a vector x in V, we can then return T1 of x or T2 of x as vectors in W. We'll define T1 plus T2 as the following rule. That is, it takes a vector x in our domain V, and it'll return the sum T1 of x plus T2 of x in our codomain W. Similarly, we can define a scalar multiplication for this set. Given a rule T1 and a scalar C, we'll define a new rule C times T1 as that linear transformation that takes a vector x in our domain to C times T1 of x in our codomain. With this in mind, we have the following two results. Say that V and W are finite dimensional vector spaces, and let's denote beta as a basis for V and gamma as a basis for W. Then V is isomorphic to the n-dimensional vector space F to the n. W is isomorphic to the m-dimensional vector space F to the m. And our collection LVW, which we saw as a vector space, is isomorphic to the collection of m by n matrices. Next, say that there is an isomorphism T going from V to W. Then we have our matrix representation square bracket T, and the statement is that if we take a look at the matrix representation of T to the minus 1, that is the inverse of T, then this is simply the inverse of the matrix square bracket T. Here's the upshot of what we're saying on this slide. If we're given a very abstract vector space V, then we can replace this with the very concrete vector space F to the n. This means that all of the hard work that we've done so far in defining abstract general vector spaces can be replaced by writing a very down-to-earth concrete vector space, such as the collection of n tuples. Let's discuss how to prove the statements. We'll start by proving the very first statement. Let's consider the linear transformation phi sub beta. This is our standard representation. And now let's write down a different representation U that will take a vector a1, a2 through a sub n and write down a linear combination of these. Then U is actually the inverse of our map phi sub beta, showing that phi sub beta is an isomorphism. This means that V and F to the n must be isomorphic as vector spaces. A similar argument shows that W is isomorphic to F to the m as vector spaces. Now let's try to do the same thing, but looking at our m by n matrices. Let's start with the linear transformation from LVW to the collection of m by n matrices by sending a linear transformation T to its matrix representation square bracket T. We can write down the inverse of such a map in a very similar way that we did this for our standard representation. Simply put, if we're given an m by n matrix, then we can express this as a linear combination, as a collection of linear combinations, by just writing things in a clever way. It is clear now that this psi is the inverse of our map phi, and therefore we see that our map phi, that is the map from our LVW to the collection of m by n matrices, is an isomorphism of vector spaces. Let's now prove the second statement. Let's say that we do have an isomorphism T. Well, we know that the inverse of T exists and is also a linear transformation, so let's consider T inverse circle T as the identity map and T circle T inverse as the identity map. We know now that the composition of maps simply corresponds to matrix multiplication. But by staring at these matrices, square bracket I from beta to beta, we see that this is simply the n by n identity matrix. It follows then that our square bracket T inverse must be the inverse of our n by n matrix square bracket T. We'll come back later in the breakout problems to discuss a little bit more of what we mean by the identity matrix and what we mean by the inverse of a matrix. Let's first go over some motivating examples before we go any further. Let's say that V is the real plane. We know that one basis of this is the standard basis, so for any two real numbers a and b not both 0, let's write down another basis and call this beta prime. We know that we can express any vector lowercase v in our vector space capital V as a linear combination of elements from the standard basis. But of course we can also do this for our new basis beta prime. Once we figure out what the new scalars are for this linear combination, we'll call these scalars x prime and y prime, and therefore we can compute the standard representation with respect to our new basis beta prime. But we see that the old coordinates x and y can be expressed in terms of the new coordinates x prime and y prime by simply multiplying by a 2 by 2 matrix. We'll call this matrix Q. Notice that the columns of this matrix are simply the vectors from our new basis beta prime. Let's try to do the same thing now for three-dimensional space. Recall that we do have the standard basis for R3, and we can construct a different basis as follows. Let a, b, and c be real numbers such that a and b are not both 0. Then we have a new basis beta prime as you see on your screen. We know that any vector lowercase v from our 3 space capital V can be written as a linear combination of the vectors in our standard basis. But we can do the same thing for this new basis beta prime. Now the new scalars x prime, y prime, and z prime we can express by simply solving a system of equations. But now, putting all of this together, we can see how to express the old coordinates x, y, and z in terms of the new coordinates x prime, y prime, and z prime. It's simply multiplication on the left by a 3 by 3 matrix. Here you'll notice that the 3 columns of our matrix, which we're denoting by Q, are just the vectors that appear in our new basis beta prime. We're going to use all of this to write down a very general concept. Let's say that V is a finite dimensional vector space. We'll start with two bases, beta, which we'll write in terms of x1, x2 through x sub n, and beta prime, which we'll write in terms of x1 prime, x2 prime through x sub n prime. Let's denote the n by n matrix Q as the matrix representation of the identity map IV going from the new basis beta prime to the old basis beta. First, this matrix is rather easy to construct. The jth column of this matrix Q is just the coordinate vector x sub j prime with respect to the basis beta. Second, the matrix Q is invertible, and its matrix is the n by n matrix that we get by looking at the matrix representation of the identity transformation IV going from the old basis beta to the new basis beta prime. Third, we see now how the coordinate vectors are related. The coordinate vector of a vector lowercase v in our vector space capital V with respect to the old basis beta is simply the matrix product of Q times the matrix representation of the same vector V with respect to the new basis beta prime. And finally, we can piece everything together as follows. Let's say that T is any linear transformation going from V to itself. Then there exist n by n matrices A and B, which make the following diagram make sense. In other words, what's happening is follows. Let's let A be the matrix representation of T with respect to the old bases beta and beta. let's let B be the matrix representation of T with respect to the new bases, beta prime and beta prime. Then we can express B as the product of three matrices, namely Q inverse times A times Q. Recall that our mapping phi sub beta is what we call the standard representation of V with respect to beta. This is the mapping that takes a vector x from our vector space V and considers the coordinate vector square bracket of x with respect to the basis beta. The matrix Q in the previous proposition is called the change of coordinates matrix from the beta prime coordinates to the beta coordinates. Let's take a look at a specific example to get a better idea of what's going on here. For the moment, let's say that beta is the standard basis and V is our collection of n tuples, namely f to the n. Then we know that each vector e sub j prime, perhaps from a new basis beta prime, is just equal to the representation that we had in the standard basis beta. Let's say that the coordinates of e sub j prime are q sub 1j, q sub 2j, all the way down through q sub nj. Again, this will be the representation in the standard basis. Then our matrix Q we find by simply placing in each of these vectors as the columns of our new matrix Q. Finally, if A and B are n by n matrices, we'll say that B is similar to A if there exists an invertible matrix Q such that B equals Q inverse AQ. This is exactly the last part of the previous theorem. In this case, we'll write B squiggly tilde A, really just meaning to say that B is similar to A. We'll state without proof that this is an equivalence relation. Let's discuss the proofs of these statements. First, let's consider the identity map I sub V going from our vector space V to itself. While we want to keep track of the bases, the old basis beta and the new basis beta prime, let's express each of the vectors in our new basis beta prime as a linear combination of the vectors from the old basis beta. We'll find some scalars q sub ij. By simply staring at this, we realize that our matrix Q, that is our change of coordinate matrix, we find just by looking at these scalars that we have here expressing the vectors in the new basis beta prime as a linear combination of the vectors from the old basis beta. Now let's show the second statement. We know that if we simply take a look at the composition of our mapping I sub V, then nothing really happens because it's the identity map. But what will happen is a statement about the product of the matrices that we have going from the basis beta to beta prime. It's easy to check that the matrix representation of I sub V going from a basis to itself is just the n by n identity matrix. So using the previous results, then we see that the inverse of our matrix Q that we had on the previous slide will just simply be the matrix representation. Instead of going from beta prime to beta, now goes from beta to beta prime. As for the third statement, this is just simply a restatement of the way that we've set up all of our notation. Let's now show the fourth statement. We have the following expressions. Q times B, by the way that we've set up the definitions of Q and B, correspond to the matrix representations going from beta prime to beta times the matrix representation of T going from beta prime to beta prime. Now we know that the product of these two matrices is what we get from the composition, but because IV is simply the identity map, then we see that nothing's really changing. But now we can express this once again as the product of matrices, and again, if we stare at our definitions, we see that this here is A times Q. Recall that B is the matrix representation of our linear transformation T in the new basis beta prime, whereas A is the matrix representation of our linear transformation T with respect to the old basis beta. Since Q times B equals A times Q, we can multiply by Q inverse on the left to yield that B does indeed equal Q inverse AQ. Thanks for listening.